How fast does a ball drop? More than 300 years ago, Galileo noticed that when he dropped a ball from the top of a tower, the ball gained speed as it moved downward. That is, a free-falling object does not have a constant speed while falling. Well, how do we square that with the formula that we know and love well, distance equals rate times time? Well, if distance were feet, time in seconds, then the rate is speed, and it's feet per second. Let's sketch the base of our Tower of Pisa, and also let's sketch in the height, which is 186 feet. Suppose that Galileo noticed it took 3.4 seconds for the ball to hit the ground. Then, if he did the math using the above formula that we have, distance equals rate times time, which is also the same thing as rate equals distance divided by time, then he would take the distance 186 feet, divide by 3.4 seconds, and that would be the speed. So the thing is that this is an average velocity, an average rate of change. It's not the same rate of change, though, throughout the time that the ball is falling. Nearer to the top, where Galileo dropped the ball, the velocity is a little less than 54.7 feet per second. But when we look at the bottom half, after about halfway through, the bottom part would be more than 54.7 feet per second. So on average, we do get 54.7 feet per second for the whole journey all the way to the bottom. In this problem, we want to find the average velocity over particular time intervals for a cyclist traveling on a bike. Let's go ahead and plot the points from the table. The horizontal axis marks time in seconds, and the vertical axis marks meters. Now I'll connect the points in a nice smooth curve. The graph is increasing, but not at a constant rate. Some parts of the graph are steeper than others. We call this slope, and we'll be studying slope throughout Chapter 2. Okay, let's go back to the problems where we were to find average velocity. Let's look at the first interval from 1 to 3, and let's remind ourselves what those ordered pairs would be from the table. Let's calculate a change in distance, so subtract the distances, and a change in time, and subtract the times. What we get then is 9.3 meters over 2 seconds. And when you divide 9.3 by 2, then you get 4.65 meters per second. That's the average velocity. Now moving to the next interval, 2 to 3, again reminding ourselves what were those ordered pairs in the table. We want to think of this as a slope, and we have a slope of the change in the distance over the change in time. And the calculation results with 5.6 meters over 1 second, and that gives us, of course, 5.6 meters per second as the average velocity. For the next couple, you could pause maybe this video and do them yourselves and come back and see what the results are. Okay, welcome back. For the interval 3 to 4, we would take the y values, which are 17.7, subtract 10.7, and below we subtract the t values for minus 3. We end up with 7 meters per second. For the interval 4 to 5, likewise 25.8 minus 17.7 for the y values over 5 minus 4, we get 8.1 meters per second. I hope you did good on that. Now let's have a look at the graph, and specifically at the interval 1 to 3 and what kind of meaning that has in the graph. Let's connect the interval t equals 1 to t equals 3. We see a line that we've just created, and that line has a specific slope, and that slope is the average velocity of 4.65 meters per second. And this is what we call a secant line when we connect 2 points on a otherwise curve. But if we want to find the slope at exactly 3, this is called the instantaneous rate of change. And I'm going to now sketch a slope that best mimics just around that point 3, sketching this line. This is called a tangent line. And now what I'm going to do is sketch another secant line where I'm going to connect 3 to 4, and that's the blue line. So I'm back to secant lines now. So I have 2 secant lines and a tangent line. How do I find then the instantaneous rate of change? What I'm going to do is I'm going to average the average velocities. So the secant line on the left from 2 to 3, and then the secant line on the right from 3 to 4. Those slopes, I'm going to average each of those slopes and come up with something that is the best approximation that I can get for the instantaneous rate of change at t equals 3. So in averaging, we get 6.3 meters per second, and that then is what answers the instantaneous rate of change. We use this new symbolism, S prime of 3. S prime of 3 means instantaneous rate of change at 3. And we conclude at 6.3 meters per second. In summary, we've used average velocity of the points close to t equals 3 to find an estimate for the curve's instantaneous slope at t equals 3. Thanks for watching, and subscribe for more great math videos.